So welcome back to Physics of Music. Today I want to talk about why it is that real oscillators don't keep the same amplitude forever. So if we look at the oscillator behind me, then it's oscillating with some amplitude and that's staying pretty much constant. So it's looking like a sinusoidal function of time, the displacement that is. But if we wait a while, then eventually that amplitude is going to decrease and decrease and decrease, and eventually the amplitude will go to zero and that thing will be still. So a more dramatic example would be the one shown here in the picture, where the amplitude decreases from, in this case, 8 whatever units it is to down all the way down to 2 in a time of apparently 10 seconds. And so we want to understand why it is that these amplitudes decrease. And so to do that, we need to talk a little bit about energy. So we talked about energy early on when we were introducing the idea of a conserved quantity in physics. And we said that for a physical system in an environment with a time translation symmetry, meaning that if you wait some amount of time, then the environment is the same as before. So in that kind of environment, then any physical system will have a quantity associated with it that we call energy that just doesn't change with time. And the interesting thing about energy is that it can come in various forms. So we talked about just objects in outer space, isolated objects, and we said that the mass of an object is an indication of the energy that that object has when it's not moving. So just a stationary object can have some energy. Then a moving object can have additional energy that we call kinetic energy. And during interactions between objects, what happens is that energy can transfer between the objects, and it can also change its forms. You can change from one type of energy to another type of energy, and just overall, the total energy has to remain constant. So maybe before we apply this idea to our oscillating spring system, it'd be interesting just to talk about the kinds of energy that we have in general. And so I mentioned kinetic energy, that a moving object generally has some energy. And then the other kind of energy that we didn't talk about before when we were just talking about isolated objects, another major type of energy that you can have is what's called potential energy. So as an example, we can talk about gravitational potential energy. And so this has to do with, say, the location of an object relative to another gravitating object. So let's say the Earth. So this object, if I raise it up relative to, well, the center of the Earth or just the ground, we would say that it has some kind of additional energy compared to before. And the way we can see that is that if I let this object go, all of a sudden it starts moving, and so its kinetic energy is increasing with time. And so that kinetic energy must have come from somewhere, and we say that it comes from the gravitational potential energy. Okay, so potential energy in general just has to do with the locations of objects. In this case, if you have two objects that have mass and you move them further apart, then that system has more gravitational potential energy, and that could be later released by those coming together, and then they would speed up and get kinetic energy. We also have another kind of potential energy that's associated with electric charges that objects might possess. Okay, so at the molecular level, then everything is composed of these charged particles, electrons and protons, and depending on the configuration of all of those, you could have more or less electric potential energy. So a simple example of that is if you had just two charged objects with the same charge, and if you moved those objects together, well, then we know that like charges repel each other. And so bringing two charges that are the same together, like two electrons close together, that would be adding potential energy to that system. And if you let them go, they start moving apart and they get faster and faster. And so that's an indication that you must have stored some energy somehow, because they later get kinetic energy. Similarly, if you took a plus charge and a minus charge, like an electron and a proton in an atom, then those want to be together. And so bringing them apart is what adds potential energy to this system. Okay, so just the general takeaway message is that potential energy is something that has to do with the configuration of a system. Where are the objects relative to one another? And in the case where they have mass, which is true for most objects, you have gravitational potential energy. In the case where your objects have charge, then there's also this electric potential energy. Okay. And so those are the most, that together with kinetic energy, those are going to be the most important kinds of energy that we'll be talking about. So let's apply this to our discussion of the oscillator here. And it's still going. I'm going to move it up and down again. I want to avoid, for this discussion, talking about the gravitational potential energy in our oscillator, because for the purpose of talking about musical instruments, generally gravity is not playing a big role in the functioning of musical instruments. And so what I'd rather do is talk about the oscillator that we would have if we just had like a horizontal spring. So maybe an object on a horizontal spring. I am just going to check something out. All right, that's great. Sometimes I get nervous that I forgot to start the recording and that I'll talk for 20 minutes and then I'll finish and then there won't be any recording and I'll just have talked to the screen for a while. But this time I started the recording. So I want to consider this horizontal oscillator where you have a spring. Let me get my demo spring here. Okay, so a spring like this. And in this case, if we had a mass attached to this spring, it could definitely oscillate back and forth even without gravity. Let's say that the mass was sliding on a surface without much friction. Okay, and so we want to think about what kind of energy is present in this oscillation. So obviously some of the time we have kinetic energy because the object is moving, the mass on the spring would be moving. So in the middle picture here, then we definitely have kinetic energy. But the interesting thing is that other times we don't have any kinetic energy. So when the object is compressing the spring the most, so that's the maximum displacement to the left, then it stops and then it starts moving the other way. And then when it gets to the furthest point to the right and the spring is stretched as much as possible, again, the object stops and then it will move back the other way. And so those times when the object is stopped, what we must conclude, if we believe in energy conservation, is that the kinetic energy that the object had when it was moving must now be stored somehow in the configuration of the spring. So either compressing a spring or stretching a spring must store potential energy in the spring. Okay, and so that must be what's happening in the oscillation, that you have potential energy stored, it's released to kinetic energy as the object starts moving, and then it gets stored in potential energy when the spring is stretched out. Let me just convince you with a demonstration that in fact the spring does store energy when I compress it or stretch it. And so I can just simply stretch out the spring and then I'm just going to let it go. Okay, and it actually flew up all the way to the ceiling there. So that just from being stretched out and then I let it go, it was able to develop all of this kinetic energy. And so that must have come from somewhere. It must have been stored in the spring when it was stretched out. And ultimately, this actually boils down to this kind of potential energy I was talking about with the arrangement of charges in an object. And so when I stretch this thing out, basically some of the plus and the minus charges are further apart than they would want to be. Maybe some of the different electrons are closer together than they were before. And so you've added potential energy by changing that configuration of molecules. Okay. Similarly, I can show you that by compressing the spring, then we store potential energy. So it's easier to compress it if I compress it into this tube. And so then if I let that go, then it pops out. So we can, again, store energy in the potential energy of the spring by compressing it. And then I let it go, and it converts to, there we go, kinetic energy. Okay. So just so you know, this won't be extremely important for this course, but just so you know, there is a simple way to quantify the amount of energy in kinetic energy and in potential energy for our oscillating system. And so just in general, and this is something you may have encountered in previous physics courses, we can say that the kinetic energy of an object, or at least one that's moving significantly slower than the speed of light, kinetic energy of an object with mass m and speed v is a half mv squared. For our spring system, if we want to know the potential energy relative to the situation where the spring is neither stretched nor compressed, then we can say that it is 1/2 times the spring constant that appears in Hooke's law times the displacement from equilibrium squared. So it's interesting that in both of those things, you have a slightly more complicated dependence where, for example, if I double the velocity, I get 4 times as much energy. Or if I double the stretching, it's actually 4 times as much energy. So I'm actually going to explain that or motivate it in a separate video has a little bit more mathematical sophistication, so I decided not to include it in the main line of the lecture. But if you want to check that out, I'll put a link below, and you can learn about that. Okay. So the main thing that I wanted to get at by showing these formulas, that the potential energy is related to the square of the displacement and the kinetic energy is related to the square of the velocity, the main thing I wanted to get at was this result. And so what it tells us is that it allows us to compare 2 different oscillating systems and compare their energy. So if I think about this particular system here, hopefully you can see that. If I have an oscillation with 1 amplitude, and then if I double the amplitude, and I want to know, well, how much more energy is there in that oscillation with double the amplitude? Well, I could just evaluate the energy at the place where the object is not moving. Okay, and so in that case, all of the energy is potential energy. The displacement is maximum, so that's when the displacement is equal to the amplitude. And so we could evaluate the total energy there as 1/2 k times x squared, which is 1/2 k times the amplitude squared. There's no kinetic energy, it's all potential energy. And then we can use our formula that I just mentioned on the previous slide. Okay. And so what you learn, and this is kind of the big takeaway message here, that if we have an oscillating system and we double the amplitude, that corresponds to having 4 times as much energy involved in the oscillation. Okay, so there is this relation between amplitude of oscillation and energy stored in the system, and it's a little bit more complicated than you might have thought. If you double the amplitude, you quadruple the energy. Okay, so that was pretty much what I wanted to say. Just one more visual in case it helps. The oscillation of the spring can be represented in terms of its energy by this diagram here, where I've shown how much potential energy is there, how much kinetic energy is there. And this is assuming that we're not losing any energy to the surroundings. Okay, so in the top diagram, this is when the spring is maximally compressed. There's no velocity, and so it's all potential energy. And then as it starts moving, you see that you have partly potential energy, partly kinetic energy. When it's at the equilibrium position, then you just have kinetic energy, and then it transitions again to partly potential, partly kinetic, and then all potential. And then it just oscillates back and forth. So you see this interesting transfer of energy back and forth between kinetic and potential, but the total energy is conserved, assuming that the amplitude stays the same. Okay. But now we're ready to think about the question that we started with. Why does the amplitude sometimes decrease? Why does the oscillator over here eventually slow down? And because we've just established the relation between amplitude and energy, what we know is that as the amplitude decreases in a real oscillator, it must be that some of its energy that it started with is not there anymore. So that energy, because it's overall conserved, it must be going into some other part of the, well, maybe the environment or some part of the system. And generally speaking, there could be various reasons for that. So one of them might be that it is moving the air around it. Okay, so that is very important when we're thinking about musical instruments. If I have this tuning fork and I start it going, and so it's audible, and it wouldn't be audible unless it were actually having some effects on the surrounding air, as we'll talk about next week. So it's giving up some of its energy to the surrounding air, and that allows the sound to be transmitted and for us to hear it. Okay. And so necessarily, if it's doing that, then the amplitude of vibration of the tuning fork must decrease. There are other kinds of energy loss that maybe aren't so useful. It might be that the tuning fork itself is heating up a little bit as it vibrates. Okay, that's another important kind of energy. We talk about the heat of an object, and ultimately that is just the kinetic energy of the molecules. So when an object heats up, then the molecules are just moving faster. So we have this transfer of energy to do with the large scale motion of the tuning fork down to motions of the molecules in the tuning fork. Or in the case of sound, the molecules in the air. Okay. The last thing I wanted to mention today is that we can also add energy to oscillating systems. Of course, we can do that by just, say, a single event at the start where we talked about hitting the oscillator, hitting the mass with a hammer, or displacing it with our hands. So those are two ways we can just add a bunch of energy all at once. But I wanted to mention a third way we can add energy to the system that turns out to be very important for musical instruments. Okay, and so just going back to our discussions of, say, stringed instruments, we talked about plucking, and then we talked about a hammer hitting a string. But what about a violin? What about a bow being dragged across a string? And so that's something that is, instead of adding energy all at once, it's kind of continuously disturbing the system. And so that's an example of what we would call a driven oscillation. So just to end this lecture, I wanted to demonstrate what I mean by a driven oscillation. And so we can demonstrate with our setup over here. So what I'm going to do is first stop the, so let's turn this so I'm in here. So what I'm going to do is first stop the oscillation. Okay, and then when we talk about a driven oscillation, what it means is that we can just apply an oscillating force ourselves. Okay, so I just go up to this thing and start shaking it up and down. Okay, while it's starting to move, it's oscillating a little bit. Okay, or I could shake it like really slowly up and down, and then it's oscillating up and down really slowly. But there's one very, very interesting thing about these driven oscillations, which is that if I go in and I start shaking it at the same rate, at the same frequency that it wants to vibrate at. Remember, there's this natural frequency for our object. If I go in and shake it with just that frequency, or a frequency close to that frequency, what I end up with is I end up getting a much larger amplitude. I end up kind of very efficiently transferring energy to this system. And so I wanted to demonstrate that. I'm going to put my hand up the top, and I'm just going to move it up and down very, very gently, but just at the right frequency to match the natural oscillation frequency of this object. Okay, so I'm barely moving my fingers here. Hopefully you can see that. And yet, the object is starting to oscillate quite dramatically. Okay, there we go. It's probably going to hit the desk soon, so I will stop. Okay. And so what that demonstrates, if I come back here, so what that demonstrates is the phenomena that we call resonance. And that is going to be extremely important for our discussion of music in the future. To summarize that, just to say it again, what we did was to apply some force which was oscillating up and down. And there was a particular frequency that I get to choose. I get to choose how fast I move my hand up and down. And if that frequency matches the natural frequency of the system, okay, the frequency that it will oscillate on its own, then we end up getting this very large amplitude oscillation. Okay, and so this is the phenomena of resonance. We're going to talk more about it next time, and we'll see lots of applications of this in music in the future.